Hello everyone. Today we'll discuss about the basic information of the worm and worm wheel and about the design steps of worm and worm wheel gear. Okay. So initially, first of all, we'll discuss the basic terminology. Rather than terminology, we will discuss first what is the worm wheel and worm gear. So we know that the worm and worm gear drive are used to transmit a power between two non-intersecting and perpendicular axis shaft. The worm gear drive is used as a compact arrangement for high reduction ratio condition. Normally, the worm is generally made of uh, a cylindrical shape, and it is normally a driving member. Uh, the shape is like a screw, okay, where the grooves are made up of trapezoidal or acme thread. The worm may be left-handed or right-handed and maybe single start or multi-start. The worm gear is similar to that of helical gear, except that the face is concave to envelop the worm. The worm and worm gear have same same hand of helix they will while engaging. It should be required. The meshing action in the worm and worm wheel drive is a combination of sliding and rolling. With respect to sliding, predominate at the high reduction ratio, as they are non-intersecting as well as perpendicular axis. The both action can be occurred based on the angular movement. Then the worm and worm gear are similar to that. Worm gear is similar to that of crossed helical gear, but the gear capacity or load carrying capacity of the worm gear is more than that of helical gear, because there is a huge friction as well as the contact area is more, and because of that it can be happen. uh, Next one, the worm gear is generated by hobbing process as well as these milling process with the help of a single point cutting tool or milling tool, with help of disc by using disc cutter. Uh, the worm threads are normally finished by using grinding machine. Now discuss about the advantages and disadvantages of worm gear drive. As compared with the other, it is very compact, high reduction ratio. In a single stage, it can be reduces speed up to 70 as to 1. Because of high reduction ratio, frictional forces are more, and because of that, the speed is very less. And because of same condition, the operation is very smoother and silent. It can be designed for irreversibility or for self-locking, and because of this condition, due to this reason, they are used in hoisting application. Next, the limitations of worm and worm wheel are as follows. The first one, efficiency. As there is a lot of friction, the power whatever they are creating, that uh, we are exhausting in to overcome the friction. That's why the efficiency of this drive is very less. Because of high friction, there is a heat generation problem is occurred with this drive. About the material cost, the material used for worm and worm are different, because there are sliding contact as well as rolling contact, and because of that the high friction is generated, and it is the anti uh, resistant property uh, should be there with the material. So that's why the two different materials are normally used. And uh, material normally used for worm is brass, and for worm wheel is steel. And the cost of brass is very high. Initial cost of brass is very high. That's why the initial cost of the total drive is very high as compared to the other one. Then power transmission capacity is low. Yes, as I said, the efficiency is very low. The whatever the power they have generated, and that most of the power is we are introducing to overcome the friction, and because of that, the power whichever they transmitted to the output shaft is very low. Okay, now uh, morely we directly go to the design. Okay, in that design we will discuss terminology as well as other things. Okay, so the design problem is given. A worm and worm wheel drive is required to transmit a power from an electrical motor rated at 11 kilowatt and 440 rpm with the reduction ratio of 15. The power is supplied to a belt conveyor which operates in about 12 to 14 hours per day. So what we need to do, we need to select a suitable material and design stresses. Secondly, we need to design worm and worm wheel to satisfy the strength and wear criteria. Indicate the constructional details for the worm and worm wheel for economical design. Draw a neat sketch of assembly including all leading dimensions. Okay, so you can draw a basic diagram uh, like this one. From PSG, you can refer and draw a initial diagram. Yes, so this one you can directly draw, which can shows the terminology as well as basic dimensions of the worm and worm gear pair. Okay, so now we will discuss about the first steps, different steps. So first step is to select a system and the strength calculation. Based on the strength calculation, we have to select the weaker element. So initially we have selected tooth system is a 20-degree involute full depth involute system. Then closed system, yes, to avoid the abrasive wear as the foreign particles will trap in between the worm and worm wheel while meeting, so it can be create an abrasive wear. So and because of there are high heat generation, the lubrication required is more continuous lubrication is required. So that's why the closed system we are considering. About the quality of the gear, we needed high precise quality of gear because due to high temperature there is a possibility of seizing as well as pitting. Okay, so to avoid this one we need to high quality precise gear. About the correction of the gear, there is a we have considered normal correction is of screw and gear is equal to 0. Next step is to select the number of starts for worm. Now the number of starts we can select by using AGMA relationship, that equation we have Z1 is equal to 40 divided by I plus 1. So transmission ratio, we know that I is a transmission ratio which is a 15. So Z is equal to 2.5. But from standard value we know that Z is equal to 1, 2, 3, 4. So we are selecting Z, that is a number of starts is equal to 3. As per rule above with respect to the transmission ratio, the if the transmission ratio is in between 10 to 20, you need to select the number of start is equal to 3. Then number of teeth on worm wheel. Okay. So number of teeth on worm as we get that is a 3. So number of teeth on worm wheel Z2 is equal to Z1 into R. Okay. So what we get Z2 is equal to 45. Number of teeth on worm wheel is equal to 45. Then we have to check the condition that these Z1 plus Z2 should be greater than 40. Okay, which is we have found from PhD page number 8.52. Okay, so here they have given the condition for factor y that z1 plus z2 should be greater than 40. Okay, so in our case the combination, or you can say z1 plus z2, you get directly value is equal to 3 plus 45 is equal to 48. Okay, so we are satisfying this condition. Now next one, we have to find out the one more factor that is called as a diametrical factor, or we can say diametrical quotient. So it is nothing but a ratio of diameter, that is a pitch circle diameter of worm divided by module, axial module you can say, or transverse module or module. Okay, so that is the ratio we have denoted by Q. Normally, Q is equal to 11 is chosen. Referring the PhD page number 8.44, I will just show you. So here they have written over here. So value of Q you can determine from the table number 6 if you have the value of dm and transmission ratio. Initially it is chosen is equal to 11. Okay, now we need to choose what actually it can be happen if the diametrical quotient, or you can say diametral coefficient is changes. Okay, how it can play an important role if the value of Q is larger, then the strength and the rigidity of the worm shaft is higher. Okay, and if it is smaller, then the efficiency of the worm gear pair is higher. Okay, if you increases the value of Q, then the strength of the worm get increases. If you reduces the value of Q, the efficiency of the worm gear is get increased. Okay, so it is normally depend upon the value of two angles. Okay, so here I will show you. Okay, in this you can just observe there are two angles, alpha, gamma and beta. Okay, so gamma and beta, it is the combination of two helix angle. So beta is a helix angle with respect to the screw as well as with respect to the gear, and the alpha is the leap angle. Okay, so alpha, the helix angle is made by the helix with an axis of rotation, or it is an angle made by the teeth with the axis of rotation, and it is generally about to 40 more than 45 degree, but in the shafting condition is a perpendicular, so the helix angle beta 1 for gear, sorry, for worm, and beta 2 for gear. So combination of beta 1 plus beta 2 is equal to 90 degree. Okay, so the combination of this and the leap angle, the, or you can say lead angle. Okay, so the lead angle of the worm, It is an angle made by the helix of the worm with the plane perpendicular to the axis of worm, okay, which is shown in a figure. Okay, so the helix angle, or you can say beta 1 is equal to that leap angle. Okay, so this combination we have considered for design. Now next, as we discuss about the Q, if the value of Q is lesser than 8 mm, the wear will be fail, worm will be fail, and if the value of Q is greater than 13, this design is called as a over design. Now, based on the number of start and diametral factor, we need to find out the lead angle. As I previously said, we can find out the lead angle best by using these two factors. Referring PhD page number 8.45. So in this table, you can find out the lead angle. Okay, so our number of starts are 3, so we have to choose this column, and the value of Q is 11, so we have to consider this column. Okay, so combination what we get, the lead angle is equal to 15 degree 15 minute and 88 second. Okay, so see, this is nothing but gamma as well as beta 1. Okay, here I have mentioned that beta 2, sorry, that was my mistake, beta 2. So gamma is equal to beta 2, but the combination of beta 1 plus beta 2 should be 90 degree. So helix angle with respect to the screw, so this angle we have find out with respect to the wheel, that is a beta 2, and for with respect to the screw, or we can say worm, we need to find out, that is 90 minus this 15 degree 15 minute and 18 seconds. Okay, we have converted it properly, and what we get, the helix angle beta 1 is equal to 745 degree. Okay, what we seen that beta should be greater than B2. Okay, so if if this condition occurs, the efficiency uh, is normally increasing with respect to the helix angle. Okay, now next we need to find out the virtual number of teeth. Referring page number 8.55, the virtual number teeth ZV1 is equal to Z1 cos cube beta 1. Putting values, what we get for a worm, the virtual number of teeth are 164.695, but and in case of worm wheel it is 50.11. Now about the material selection. As we discussed previously also, uh, there is a question that why dissimilar materials are used for worm and worm wheel. In the worm wheel gear pair, the motion is predominantly sliding motion, and hence there is a considerable friction. Therefore, the worm gear is made of material having anti-scoring and anti-frictional properties are there. So that's why we are selecting the material like cast iron or bronze. Okay, and for worm, uh, the worm also subjected, you can say worm. Previously we have discussing about the worm. Now we have to discuss about the worm gear. The worm gear is normally subjected to for bending and torsion, and the material which having higher strength and ductility, like materials like plain carbon steel or alloy steel. So that because of these two conditions, we are using steel material for worm wheel and bronze material for worm wheel. Worm made up of steel and worm wheel made up of bronze. Okay. Uh, Now next, why worm gear is always governs the design. Uh, Here, uh, it it means that कि जो भी डिजाइन है वो डिजाइन हम लोग वर्म गियर डिजाइन से कैसे वर्म वर्म व्हील डिजाइन से स्टार्ट क्यों करते हैं. As we discussed previously, it the what about the material, the worm have a material about the steels, and worm wheel we are making from bronze material. So these are two different material. Out of that, steel is a harder material and the bronze is very softer material. As we know that the softer material is always fail as early rather than harder material. तो इसके वजह से जो भी जो weaker element बनने वाला है, that should be the worm wheel. Okay, we will check by mathematically how this statement is true or false. Okay, so the bending material, rather than first we have selected the material for worm is a steel, or you can say 40 Ni, 2 Cr, 1 MO, 20 I, 28, or C45. Okay, and for worm wheel it is a bronze. So referring PhD page number 8.5, the bending strength, design bending strength for C45 material is 1350 kg per centimeter square. Referring page number 8.45, as the manufacturing process used for worm wheel is sand casting and material is a bronze, the bending design strength is equal to 500 kgf per centimeter square. Now Lewis form factor, yes, we need to calculate Lewis form factor for checking the weaker element. The equation is on PhD page number 8.50. Okay, the equation based on the 20-degree full depth involute profile system, YV is equal to pi into square bracket 0.154 minus 0.912 divided by 1 Z1 or Z2. Okay, depend upon the worm or worm wheel form for which we have to calculating the Lewis form factor. For worm, we have found the Lewis form factor is 0.4664, and for worm wheel it is 0.4266. Now we need to calculate the weaker element. The product of design bending stress into the Lewis form factor will give the strength. So that based on that strength comparison, we need to decide the weaker element. Sigma B1 into YB1, what we get? 629 kg per centimeter square. Sigma B2 and YB2, what we get? That is 213.3 kg per centimeter square. So it indicates that the worm is a harder than, or the strength of the worm is more as compared to the worm wheel. So here we need to design a worm wheel first, because we are using softer material for manufacturing the worm wheel. Now next step, to determine the module. So here we are using axle module, referring the PhD page number 8.44. Okay, so in PhD page number 8.44, this one is the equation, that is mx is equal to 1.24 cube root of design mt, that is design twisting moment transmitted by the worm wheel in a kgf centimeter, divided by z, this is the number of teeth on the worm wheel, q, that is a diametrical factor, then yv Young's modulus, Lewis form factor, and design sigma b. Okay, so out of that we know design sigma b, then y, q, and z. We need to calculate about to mt, so that is a design twisting moment transmitted by worm wheel. So how we can calculate mt? Here the relation is given, mt into kdk. Okay, so first of all we look out for kdk. Kd is the load concentration factor. When the load is almost constant, it is considered as a 1. And Kd is a dynamic load factor is equal to 1 for the velocity lesser than 3 meter per second. Okay, so it happens with our condition. So multiplication or product of k into kd is equal to 1. Now only we need to calculate mt. For mt we need to use this equation. Mt is equal to 71,620 hp divided by n into I into efficiency. How we can calculate efficiency? Referring page number 8.46, table number 37, this one. So as we know that the value of z is 3 and the efficiency for that number of starts is 80% to 92%. We are considering it's about to 85%. Now next value of I we have value of small n, this is the 1440. Now efficiency का value भी पता चल गया है. Now we need to calculate the design twisting moment. Okay, so putting all the values in equation. Okay, यहाँ पे हमने क्या किया है? Rather than writing that is a value of 13.2 kilowatt, that is a 13.2 into 10 raised to 3 divided by 746. Okay, तो आपको value मिल जाएगा in HP. Otherwise you can write 13.2 divided by 0.746. Okay, so ये वाला प्रॉपर आप लोग ध्यान में रखो, आपको कैसे लिखना है उसके हिसाब से आप लिखो. Okay, so putting all the values, what we get? So the value of mt is 11,220.39 kgf centimeter. Now we need to check this. Putting all the values in the equation, and we need to calculate the module. So transverse module, what we found, that is a 5.87 mm, or you can say 0.587 centimeter. So selecting next one, standard one, either 6 or 8. We can choose 6 one also, but for more getting more strength in the design, or you can say to increase the strength, I have selected mx is equal to 8. Now we need to check this for bending stress. So you can refer PSG page number 8.44. Here the equation is given. So you can using this 11.4 equation. See sigma b, or you can say induced bending stress, is equal to 1.9 design mt divided by mx qz into yv. Okay, so after the putting all the equation, all the value in the equation, as we have all the values, we get that the induced sigma b is 176.34 kgf per cm square, as our design sigma b is 500 kgf per cm square. Okay, so hence the induced is lesser than the design. Our design is safe. Next step, we need to check the loading conditions. Okay, if the static load is greater than the dynamic load, design safe. If the wear load is greater than that of dynamic load, our design is safe. So these two conditions we need to check. For that we have to refer PhD page number 8.52. So in this page they have provided the basic equations required for dynamic load, static load, as well as only two loads. Wear load, we have to by heart that equation. I will tell you. Okay, so from this one is the equations regarding to the worm gears. Okay, so here the equation is given. Fs is equal to sigma b by b p c n divided by pi. Putting the value, what we get, sigma b by p divided by pi dn. Pi dn is equal to 1 upon mn. So after the putting this into the equation, what the equation we get? We get a total equation or final equation is sigma b into yv into b into mn. Okay, so b with respect to the empirical relation, b is equal to 0.75 d1, phd page number 8.48, table number 38. So d1 is equal to q into mx, referring phd page number 8.43, table number 35. So what we get, d1 is equal to 8.8 as q is equal to 11 and mx is equal to 0.8. Now this relation is not present in a design data book, so you have to by heart this equation. Mn is equal to mx cos of gamma. So here the value of gamma, which we have already found out, the lead angle, is equal to 15.255 degree. Mn is equal to 0.8 into cos of 15.255 degree. What we get, Mn is equal to 0.77 centimeter. So based on this value, we have to calculate the value of Fs. So we know that sigma b, that is a 500, then Lewis form factor, that is 0.4266. Okay, then value of mx we have calculated, mn we have calculated, or putting all the values, what we get, then another for value of b is the nothing but 0.5 into 8.8. Okay, so putting all the values, what we get, fs equal to 1085.39 kgf. Okay, so we have finally found the static load, initial static load. And now we have to find out the dynamic load acting on the system or a drive. So Fd is equal to Ft into Cv. Okay, they have provided equation like Ft is equal to 6 plus Vm divided by 6 in PSG. Okay, so you can refer this equation from here into Ft. Okay, so V is nothing but a velocity of gear, Vmg. So velocity of gear we can find out by pi d and by 60 divided by 1000, as all the dimensions are in mm. So you can directly find out the value in meter per second. So pi into d diameter of gear, which we can find out mx into z2, then n for wheel, it is in condition of wheel, so n2 we can find out is equal to n1 divided by I. Okay, so 1440 divided by 15, you can get value of n2. So putting all the values, what we get, the velocity of gear is equal to 1.809 meter per second. So now we have to calculate Cv. After putting value of Vmg, what we get, Cv is equal to 1.305 meter per second. Now need to calculate value of Ft, transmission ratio or transmission force. So that force you can calculate from PSG page number 8.57. Equation is given. You can for worm, tangential stress, yeah, tangential stress, that is a, or you can say axial force acting on the worm gear. So that is a 2 mt divided by d2. in just a minute. Okay, so putting all the values, what we get, ft is equal to 623.355 kgf and fd is equal to 8.11.296 kgf. As compared with the fs, the value of fd is less, so hence our design is safe and our first criteria is fulfilled. Now we will check for the second criteria. For that we need to calculate a wear load. So wear load Fw is equal to dgb into kw. It is in a PSG. Oh, sorry. This equation haven't provided in a PSG, so you need to by-heart this equation. It is so kW factor you can find out from. Sorry. It is within PSG. So here the wear load is given. Fw is equal to dg into b into kw. So kw, how we can find out the kw? So kw is a wear factor. For that we need to refer table number 43. So in a table number 43, worm is a hardened steel and gear is a bronze. Okay, and the pressure angle is 20 degree. So value of kW is equal to 5.6. Okay, and 5.6. Okay, so about the B, the relation into B and D, we have already shown that relation, that B is equal to 0.75 D1, B is equal to 0.75 D1. So value of B is 6.6 centimeter, and DG, that is a gear diameter, that is a mx into Z2. Okay, so putting this value, and what we get, the Fw is equal to 1330.656 kgf. So it shows that the wear load is greater than that of dynamic load, and the second criteria is satisfied, and hence both criteria satisfied, our design is fully safe. Now you can calculate the remaining basic values, or you can say terminal dimensions using PSG. So referring PSG page number 8.43, table number 35, you can find out the all basic dimensions of the worm and worm gear. For example, center distance, face width, then length, and then axle model, which we have already calculated, number of state we have calculated, gear ratio we have, diametrical factor Q we have, height factor you can find out, axle pitch you can find out, pressure angle that is 20 degree, lead angle which we have already calculated. Also you can find out from this equation, that is a tan of gamma is equal to Z by Q. Okay, so addendum you can find out for worm. You can find out the reference diameter, tip diameter, root diameter, pitch diameter. For worm wheel, you can find similar diameters. Then you can find out throat diameter and other parameters. Okay, so using this page, you can find out the basic dimensions of worm gear pair. So if you have any doubt, you can ask me on my WhatsApp. Thank you. Thank you very much for joining me.